Okay, let's start our lecture today. So, yeah. So last time I was unclear about the Weierstrass function. So, yeah. So, So it should be like um, a solution that a function studied in the previous case. Okay. So. Okay. So let's continue. Okay, let's continue. So okay, so we show that this f has this period omega 1 and omega 2 from last time. Okay. So now it says that and then it says that it follows that this PZ, I think it should be actually a square P minus FD. Is a constant. Okay. And then it says that and by the form of the development of the origin. Development at the origin okay. The constant is 0. Okay, let's see. Okay, so at the beginning it says that. So this is the beginning of the chapter. Okay, so I want to refer to what is this PZ. Okay, I want to find some clue of what it is. So here it says that the simplest elliptic functions are of order 2, and such functions have either a double pole with residue 0 or two single pole with opposite residues. We shall follow the classical examples of Weierstrass, who choose a function with double pole as the starting point of a systematic theory. Oh, okay. We may as well place the pole as the origin, and since the multiplication with a constant factor is clearly irrelevant, we may require that the singular part is, it's z to the negative 2 power. Okay. If f is elliptic and has only this singularity of the origin and its congruent points, and has only this singularity as the origin and its congruent points. Yeah, congruent points means that I think it just means that yeah, so I think it just means that I think that it's find some congruent relation that simulates the structure of this omega, right? So omega is like it's as a periodic, like we just showed, right? So I think, yeah, let me just let's see how it defines elliptic function. Let's see. So okay, so first he defined the periodic to be, yeah, so he defined that. Okay, so let's do a little bit literature review. Okay, so okay, so here it says, he says that the function fz is said to be a periodic with period omega not equal to 0 if we have f of z plus omega equal to fz for all z. Okay. Oh, okay. So for instance, okay. So for instance, it's if the z has period 2 pi I, okay, and sine z and cosine z has period 2 pi. Okay, so these are wait for sine. Wait a minute. So sine z. Okay, so how do we define the okay, so yeah. If you have a 2 pi I, what do you think? So sine z is being defined as e to the iz minus e to the negative iz over 2i. Okay, so if you change it to pi, right? So then you will factor out a e to the iz. If you plus, okay, yeah, if you plus the 2 pi, and then oh, so yeah, it will be divided by e to the 2 pi I, and then e to the 2 I is equal to 1. Okay, okay, then it's the same. Okay, so we have pure 2 pi. Okay. Yeah, I think the same thing for cosine, but yeah, so here didn't say what's the no, I think okay, it's like the same thing. Okay, but I think it's a minus, it's a plus, and then it's over 2. Okay. 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 All right. Okay, so yeah, so he defined the periodic and give some example of periodic function, and then okay, and then wait, what? We shall be considered in a region omega which is mapped onto a cell by the translation z to z plus w. Okay. Oh. Oh. Okay, so okay. Okay, so okay, so here he is saying that the elliptic function and the doubly periodic function are interchangeable. Okay. Okay, so okay. Okay. Okay, so maybe I should start at yeah. Okay. Yeah. I think let me think. I think I should start at the very beginning, the elliptic functions, but okay, anyway, let me okay, so here he defined a so he defines the periodic. Okay. And then he says that if omega is a period, so are the all integral multiples n omega. Yes, you can show that by the induction argument. Okay, so yeah. So here omega is a period. So it implies that n omega is also a period. And also, so we call this ft as simply periodic function with period omega. Okay. So Yeah, so this is a simply periodic function. Okay. And then we also have the, I think, where did he define doubly periodic? Okay. Yeah, he says that. Anyway, I'm still trying to look at where he defines the doubly periodic, but I think we just take the take the common sense that doubly periodic means that there's another variable like W1 and W2, right? That's they're not, they cannot be scaled, right? So they must span the complex plane. Yeah, that this function is like periodic respect to these two variables. Okay. Okay, so okay, so now we understand what is the module, so the function that we are studying with. So it is the elliptic function, and then I think he is setting up some elliptic theories, some theories about the elliptic functions in the previous two chapters. Okay, and then okay, after he's setting up the theories, he's analyzing by like he says that a simple elliptic function of order 2, okay, and such functions have a double, either a double pole or residue 0. Yeah, as I said before, okay, or two single poles with opposite residues. I think he is choosing a function with a double pole as the starting point of this semantic theory. Okay, so let